Hello everyone, myself Piyush Tandil, working as Assistant Professor in Electrical Engineering Department of Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. And the name of subject is Power System Planning and Design, which comes in 4th year, 8th semester. Right now we are discussing the chapter number 1, that is Transmission Line Design, and this is the module number 1.6. So in this module, we are going to see the surge impedance loading and surge impedance, then after concept of self GMD, or we can call it as a GMR, and mutual GMD, then after mathematical formula used for electrical design transmission line. So which are the different mathematical formula that we are going to see, and the last, that is the step for electrical design of transmission line. Step for electrical design of transmission line, this is over here for. Okay, so starting with the surge impedance loading, or SIL. We can also write like surge impedance loading as SIL. So surge impedance loading is very essential parameter when it comes to the study of power system, as it is used in the prediction of maximum loading capacity of the transmission line. So however, before studying the surge impedance loading, we first need to have idea of what is surge impedance. What is surge impedance? And we are defining surge impedance as ZS. It can be defined in two ways. One is simpler and one is little bit of complex. Okay, so starting with, it is a well-known fact that a long transmission line, that is we can normally called greater than 250 kilometer, that is our long transmission line, have distributed inductor and capacitor as its inherent property. Okay, whenever we are talking about the long transmission line, at that time we have inductor and capacitor in our transmission line, that is inherent. Okay, over here this is our capacitor, this is our capacitor, and this is our inductor. This is in transmission. Whenever we are talking about the transmission line or long transmission line, at that time we have some amount of inductance that is uniformly distributed and capacitance. While we are talking about the short transmission line, at that time we can neglect our capacitance, but whenever we are talking about the long transmission line, at that time we need to consider both, that is inductance and capacitive effect. Okay, so when the line is charged, the capacitance component feed a reactive power. Okay, what is the function of capacitor? That is, it is going to feed the reactive power to the line, while the inductor component absorb the reactive power. Okay, inductor component is absorb the reactive power. Now if we take the balance, that is whenever whatever the feed of reactive power by the capacitor is going to be absorbed by the inductor of the line, so that is called as a balance condition. Now if we take the balance of two reactive power, we arrive at a following equation. So whenever we are going to balance, that is value of inductive and capacitive, both are var, that is reactive power of capacitive, and that is feeding in the line, and the reactive power of inductor, that is absorbing in the line, is going to be equal. So we can write like capacitive var is equal to inductive var. Okay, now how we are defining capacitive var? By v square by xc, that is our capacitive var, and inductive var, that is I square xl. Okay, over here we can see that v is equal to phase voltage, I is equal to line current, xc, that is for the capacitance, so capacitive reactance per phase, and what is xl? That is inductive reactance for the phase, for the inductor. Okay, so for the balance condition we can write this equation like that, and if we are going to rearrange, like v square by r is equal to xc into xl, so we can write like something like v by I, so v square by I, so over here we need to take a square root, right? It is simple as that. So v by I is equal to square root of xl into xc. Okay, we can write like xl into xc, that is under root of twice pi fl, that is the value of xl, and what is the value of xc? That is 1 upon twice pi fcl. Over here we can see that f is the frequency of the system, that is going to be constant. L is the inductance per unit length of the line. What is the value of L? That is the inductance per unit length of the line, and L, that is the line, and C, that is the capacitance of the unit length. Okay, so we can conclude that from this equation we can write like V by I is equal to under root of L by C. So this is our, what is the value of V by I? We can write our V by I as a Z, so this is ZS, and this is the surge impedance of the line. So this quantity having the dimension of resistance is the surge impedance. Okay, we can write like under root of L by C, that is ZS, that is our surge impedance. It can be considered as a purely resistive load when connected at a receiving end. Okay, consider this, which we are connecting at a receiving end, okay, of the line. The reactive power generated by the capacitive reactance will be completely absorbed by the inductive reactance of the line. Remember this statement: whenever the capacitive reactor that is generated by the line is going to be completely absorbed by the inductive reactance. Okay, then we can write like Zs is equal to under root of L by C. It is nothing but the characteristics of Zc of lossless line. Okay, we are right like a surge impedance loading. Now we are talking about the loading. We already know about the surge impedance. Now meaning of the loading is surge impedance loading is defined as the power delivered by the line. The power delivered by the line to a purely resistive load equal in value to the surge impedance, equal in the value to the surge impedance of the line. Hence we can write like that is the power delivered. So surge impedance loading is equal to root 3 into VR into root 3 Zs, or here Zs is our surge impedance. So we can, if we simplify this equation, we can write like VR square under root of L by C. This is our surge impedance loading, and the unit of surge impedance loading is either watt, or normally we are using the term megawatt. When the line is terminated by surge impedance, the receiving end voltage is equal to the sending end voltage. Okay, uh, and this case is called as a float voltage profile. So whenever the receiving end voltage is equal to the sending end voltage, at that time we can call it as a flat voltage profile, because the behavior is completely flat. The following figure shows the voltage profile of different loading case. So we need to see the different loading case. Let's see this. Okay, over here we can see that this is our supply voltage, that is Vs, that is our supply voltage, and this is our receiving end voltage. Okay, so whenever we are working at no load condition, at that time receiving end voltage is higher than the supply end voltage. Whenever we are working in a surge impedance loading limits, at that time this is called as a flat voltage. Okay, so this is called as a flat voltage. So supply end voltage is equal to the receiving end voltage. This is called as a flat voltage. Now whenever we are talking about the full load condition, at that time the receiving end voltage is lesser than the supply end voltage. Okay, the receiving end voltage is lesser than the supply end voltage. And whenever we are talking about the short circuit condition, at that time the receiving end voltage is going to be zero whenever whatever the supply voltage Vs. Okay, so this is the characteristics or behavior of long transmission line with or without the shunt reactor. Okay, now we can also define surge impedance as a square root of or ratio of the root of the admittance impedance by the admittance, and we can write like Zs is equal to under root Z by Y. Okay, over here we can write Z is equal to R plus Jx and Y is equal to G plus Jb. We can also write our surge impedance loading equation like that. So the characteristic surge impedance loading is also been defined in the same way. Surge impedance is characteristics impedance of loss free line, that we already know. Okay, now moving forward to the concept of GMD, or we can self GMD, or we can also say as a GMR and mutual GMD. Okay, meaning of self GMD: GMD is equal to geometric mean distance. Okay, what is the meaning of GMD? Geometric mean distance. Over here we have written over here the meaning of GMD is geometric mean distance. We can also write is in DS form. Okay, this is also DS. Why DS? Because GMD of self, and if we are writing DM, at that time we can call it as a mutual GMD. Okay, because M tends to mutual. Now it can be proved that mathematically that the solid round conductor of a radius R, the self GMD or GMR. GMD means geometric mean distance and GMR means geometric mean radius. Okay, GMR means geometric mean radius is equal to 0.7788 R. What is R? That is the radius of solid conductor. Now in inductance per conductor per meter is equal to, we can write this is for the transmission line. Okay, long transmission line, inductance per conductor per meter is equal to 2 into 10 raised to minus 7 into ln dm by ds. Okay, over here dm that is the mutual inductance and ds that is the self GMD. dm that is mutual GMD, and ds that is self GMD or GMR, and the value of GMD or GMR is equal to 0.7788 R. That is for the value of ds over here, and this is the unit of Henry per meter. So ds is equal to GMR, that is self GMD, is equal to 0.7788 R. We need to remember this term for future examples. Now GMR of the conductor depend upon the size and the shape of conductor and is independent of spacing between the conductor. Okay, so GMR, that is the geometric mean radius, or self GMD, is only depending on the size and shape of the conductor. It is not going to depend on the spacing between the conductor. Now next, mutual GMD, okay, that is DM. It is the geometric mean or average of the distance from one conductor to the other conductor. It is the distance between one conductor to other conductor, that is called as the GMD, mutual GMD or DM. In other words, it is simply that equivalent geometric spacing which is independent of size of the conductor. So geometric mean distance, that is for the mutual GMD, is not going to depend on the shape of the conductor, but it is going to depend on the spacing between the conductor. Remember this term. Okay, now for the single phase line, DM equal to the distance between center and center of the conductor. So we can write, like, we have only one conductor, so we can write DM is equal to D, that is the diameter of the conductor. And for the three phase line, we can write like DM is equal to cubic root of D1 into D2 into D3, that is D1, that is the distance between 1 and 2, 2 and 3, and 3 and 1. So we can write like DM is equal to D1, D2, D3 raised to 1 by 3. Now the inductance for the single phase line, we can write like single phase line, okay, over here mention single phase line, that is 2 into 10 raised to minus 7 ln dm by ds. And what is the value of dm? That is d for the single phase line, remember this term. And ds, that is we already know, that is self GMD, that is 0.7788 R, and R, that is the radius of the conductor. We can also write over here capital R or small r. Now inductance for the three phase line, that is 2 into 10 raised to minus 7 ln dm by ds, and over here the value of dm is equal to d1, d2, d3 raised to 1 by 3. Okay, because of the three phase, and value of ds is going to remain same. So let's see the table 1.13 gives the information about self GMD of standard conductor with different straits. Okay, now here is the table of self GMD or GMR stranded conductor. Okay, for the solid round conductor we can take 0.779 R. For full straightening we can consider following as a 7 straight, the value of GMD or GMR, that is 0.726 R. For the 19 straights it is 0.758 R, and so on. Okay, and over here we have mentioned the hollow straight conductor and ACSR. In ACSR we are going to neglect the steel straight. Okay, we are neglecting the steel straight because there is no current flowing from our steel, only the current is flowing from our aluminum section that is surrounded by the conductor. Okay, so in 30 straight, that is for the two layer, we can consider it 0.826 R, and so on. Okay, over here R is the outside radius of the stranded conductor. What is the value of R? That is the radius, outside radius of the stranded conductor. Remember this term and please note this down in your notebook for future uses. Okay, now we are going to see some of the mathematical formula that we are going to use while designing the electrical transmission line. So these are some mathematical formula. These are not the steps, these are the formula. So we need to find whenever we are going to design a transmission line, we have only one or two parameters, that is like total demand of what power they required and what is the distance from where we required the power consumption. Okay, distance from our powerhouse or distance from our transmission line or substation. Okay, so we have only two parameters, that is the distance and the power requirement. So for that we can find the loading on the line, that is the power, what is the power requirement and at what distance we require that power. So this is called as the loading of the line. Second term, that is the current at a receiving end. We can find the current at receiving end, that is the equation of I is equal to power in kilowatt divided by root 3 V into power factor. We all know this is the equation of the current, while V is equal to line voltage. Now inductance per phase per meter, the equation of inductance per phase per meter we already seen, that is 2 into 10 raised to minus 7 ln dm by ds. Over here what is the dm? That is mutual GMD, and what is ds? That is GMR or self GMD. Okay, line reactance per phase, that is XL. We all know the equation of XL, that is twice by FL, that is the reactance, line reactance per phase. And capacitance per phase per meter is equal to 1 divided by 18 into 10 raised to 9 ln dm by r. Over here dm is mutual GMD. Okay, and transmission line constant parameter, that are A, B, C, D. We already studied in I think electrical power system 1 and 2, that is A is equal to D is equal to 1 plus zy by 2. This is the value of A and D, and the value of B is equal to z 1 plus zy by 6 plus z square y by 120 and so on, and the value of C is equal to y into 1 plus zy by 6 plus up to. Now we are going to see the sending end voltage. The equation of sending end voltage, Vs is equal to AVR plus VIR, where A is the constant that we already find in the previous equation, and V is also ABCD parameter constant. And from that we can find the voltage regulation. After finding the value of sending end voltage, we can find our voltage regulation. That is the equation of voltage regulation is given by Vs minus VR divided by VR into 100. So we can find it in percentage. Now we are going to find the coronal loss. We have two equations, that is Peake's equation and Peterson equation. So we are going to use the equation of PC is equal to 21 into 10 raised to minus 6 F into E square divided by log D by R into K, kilowatt per kilometer per phase, and K, that is the factor of ratio, that is total voltage divided by the descriptive voltage. Okay, so E is the kilowatt in natural RMS. Okay, what is the value of E? That is kilowatt in neutral RMS. Then after D, that is the spacing between conductor in centimeter. R is the radius of the conductor in centimeter. K, that is the factor which varies the ratio of E by D, that is the kilowatt to neutral RMS, and ED, that is the disruptive voltage. Now the disruptive voltage is also defined as ED is equal to 21.1 into M0 R ln D by R. This is for the polished wire, and 0 in between 0.72 to 0.94 for rough surface conductor, and for stranded conductor we can consider it as a 0.82. We are going to follow this formula. Now sending end current, we can also find the sending end current from the ABCD parameter, that are Is is equal to CVR plus DIR, and sending end power, that is 3 into Vs into Is into cos phi. Vs we already find from the ABCD parameter, and Is we also find from the ABCD parameter. So we can find the sending end power, and cos phi, that is the power factor at a sending end side. And the surge impedance loading of the line, we can find it by 2.5 into line kV square. Now the voltage E1 across the insulator nearest to the conductor, we need to find the E1 value for finding the string efficiency. So nearest to conductor, for finding the voltage E1 across the insulator nearest to conductor. So whatever the disc, insulation disc nearest to the conductor, we need to find the voltage at that disc. So we are finding E1 is equal to E2 sin H 1 by 2 under root CE into cos H under root of CE and minus 1 by 2 divided by sin H and under root of CE, where CE, that is defined as a capacitance between insulator and earth. It is defined as a capacitance between insulator and earth, that is normally 0.15 capacitance, that is, and the value of N, that is the total number of insulator that is used in suspension type string. And for finding the string efficiency, we have the equation of E divided by N into E1, that is E, that is the total voltage that is across the suspension type insulator string, and that is the total number of string attached to the suspension type of insulator, and E1, that is the voltage nearest to the conductor at a disc. Okay, so from this equation we can find our string efficiency. So these are total 15 equations from where we are going to design our transmission line. Okay, now we can see the steps of electrical design of our transmission line. So which are the steps we are going to follow? So first, to find the loading on the line, we are going to use the equation, that is line loading is equal to power in kilowatt, that is the what is the demand of power that required, and what is the distance, at which distance we are requiring what amount of power. So from that we are finding the loading on the line. Now what is the second step? Second step is to select the required voltage level. Okay, we have total amount of power that is in kilowatt. Remember this term, we have power that is given in our example in kilowatt and distance in kilometer. Okay, so selecting the voltage level, right now we don't have any kind of voltage level, which voltage level we are going to transmit our power. So for that we are going to find the line loading. With the help of line loading we are going to select our voltage level from the table 1.1. Now table 1.1 that we already studied in previous modules, so it is like this. So here we have the line to line voltage and line loading in kilowatts. Once we find the line voltage in kilowatt, we can easily find at which suitable voltage we can transmit our voltage. Okay, so from this table we can find proper voltage level. Okay, now moving forward to the third step, that is from the table 1.2, check the length of the line according to the voltage and choose different voltage to obtain required performance. Now we need to also see the table number 1.2 to check the line length according to its chosen voltage level. So this is the table number 2 for transmission line voltage. So over here we have whatever the line to line voltage that we have selected, and this is the maximum and minimum line length in kilometer. Okay, so from this also we can find out our voltage level. Now next, to find the current at receiving end, we have the equation of IR is equal to power in kilowatt that we already have in example, it divide by root 3 kV that we already find from 1.1 or 1.2, then after cos phi. So we are going to get our value of IR. Now fifth step, that is from the table 1.8, select approximate equivalent spacing between the conductor. We need to select the value of dm in meter. Okay, we have to select the value of dm in meter. So for high voltage line, ACSR conductor will be used. You need to remember this term. For high voltage, ACSR conductor is normally used. So we are going to find from 1.8 table we have the line to line voltage. So once we selected our line to line voltage, we are going to find out at what is the equivalent spacing in meter, that is the value of dm we need to choose. Okay, so from this table we can find the value of equivalent spacing also. Now moving forward, from the table number 1.7, select nominal copper equivalent cross sectional area in centimeter square according to the current carrying capacity of ACSR conductor. Now this table we already studied in previous video lectures. Okay, so table number 1.7, from that we can find out the nominal copper equivalent cross sectional area. So this is the table number 1.7. From that we can find the copper conductor area or ACSR conductor area. Now normally for the high voltage transmission line we are going to use the ACSR conductor. So we are finding the current capacity, that is the value of I. We already have the value of I. From that current value we are going to find the copper equivalent cross sectional area in centimeter square. So once you find your ampere, suppose your ampere is 350, at that time you can select the equivalent copper cross sectional area as a 0.9675. Okay, so this is our current in ampere, and over here cross sectional equivalent area in centimeter square. So this is the table number 1.7, from where we can find the equivalent cross sectional area of the copper. Now the step number 7, that is finding the nearest size of ACSR conductor. Okay, from that table number 1.7 we are going to find that nearest size. Okay, now moving forward, following parameters are found from table number 1.6 that we already seen. The number of thread and wire diameter, the total number of thread of aluminum and steel, the approximate overall diameter, and resistance per kilometer at 20 degrees Celsius. All this detail we are going to find from table number 1.6 that we already studied. So finding the resistance of the line, the equation of resistance of line, that is equal to 20 degree resistance into line length in kilometer. So line length we already have, and 20 degrees Celsius resistance we are going to find from table number 1.6. So remember, open up your table number 1.6 and see the value of resistance. So this is the resistance of the line. Now receiving end voltage per phase, that is VR is equal to line voltage divided by root 3. So we are finding the receiving voltage phase over here, and from table 1.13 we need to select the DM self GMD, that is DS, that we already studied in previous slide. Okay, from previous slide we need to find out the alternative self GMD for stranded wire and calculate the outer radius R is equal to approximately overall diameter divided by 2. So from that we can also calculate the outer diameter R. Next step, that is step number 12, that is finding the self GMD, that is DS. So self GMD into R So see the step number 10. So what is the step number 10? From the step number 10, that is finding from the 1.13 table. So once we have find the value of self GMD from 1.13 table, that is already defined in previous slides, and multiplying it with the r. So what is the r? That is the radius. So see the radius in 11 steps. So here is the radius that we are going to calculate from this step. Okay, so multiplying both two, we can find the self GMD. Next step is finding the inductance per phase. So equation of inductance per phase, that is 2 into 10 raised to minus 7 into length of the line, that is also given in meter. We need to convert it into meter, that is given us in kilometer, into ln dm by ds, because the value of dm by ds, that is also in meter. So dm, that is the mutual GMD, and ds, that is the self GMD that we already found over here. Now reactance per phase, that is Acsr. So equation of Acsr is equal to twice by FL. So we are finding our reactance per phase. Next step, that is the impedance per phase, that is R plus J Acsr. We already know the equation. The impedance per phase, that is R plus J Acsr. Now capacitance for the length of the line, we are going to find the capacitance of the length of the line, and equation is we already seen, that is Cn is equal to line length divided by 18 into 10 raised to minus 9 ln dm by r. So line of the length, we need to convert it into meter, that is already given in kilometer. So we need to convert it into meter, because the value of dm and r is also into meter. So we are going to find okay, over here the value of r is in centimeter, that's why we are going to convert the value of dm is into the centimeter. So see the step number 11 that we already seen in the previous slide. Now next step is to find the y per phase, that is twice by fcn. This is the value of y, and step number 16. So cn is founding from the previous step, and right now in 17th step we are going to finding the value of y. And now time to find the ABCD parameter, because we have our z and y. Okay, so finding ABCD parameter constant, d is equal to a is equal to 1 plus zy by 2, b is equal to z 1 plus zy by 6 plus z square y square by 120, and c is equal to y 1 plus zy by 6 plus z square y square by 120. Also find nominal t and pi method. Okay, this is how we are going to find. And 19, find the sending end voltage. So we are going to find the sending end voltage by the equation, that is Vs is equal to AVR plus BIR. And for finding the voltage regulation, after finding the receiving end voltage, we are finding the voltage regulation, that is Vs minus VR divided by VR into 100, that is in the percentage. Okay, so check the voltage regulation, that is within the permission limit, that is 12.5. if it is going to exceed, at that time we need to change our selected voltage level. Okay, so voltage regulation need to be in 12.5 permission limit or not. If yes, that finding the coronal loss. If no, so if the limit is going to be exceeded, at that time we have to select a higher voltage level and repeat all the steps. So if the voltage regulation limit is either within the 12.5, at that time we need to find the coronal loss, and we already know the equation of coronal loss. So that is the for finding the coronal loss, we need to find the disruptive voltage. So equation of disruptive voltage, that is 21.1 into m0 into r into del ln d by r, kV, that is line to neutral. Okay, and r is the radius in centimeter, and d is the distance between conductor in also centimeter. Now m0, that is the surface factor. M0, that is the surface factor. For polished wire, M0 is equal to 1, and for rough conductor it is going to be in between 0.92 to 0.94, and stranded conductor we are normally using 0.82. Now finding the ratio of E by ED, that is line voltage per phase divided by the disruptive voltage, the value of E by ED, that is the K, that we already seen in the previous equations. Okay, that is the equation of coronal loss. Now from the table we are going to find the Peterson's formula, and Peterson's formula, that is 21 into 10 raised to minus 6 F E square divided by log D by R whole square into K into 3, because of the 3-phase line, kilowatt per kilometer per kilo phase. And check the coronal loss within the permissible limit or not, and it should not exceed the value of 0.8 kilowatt per kilometer. Okay. Now what is the step number 24, that is finding the receiving end current. So Is, that is equal to C into VR plus D into IR. Now power factor at the receiving end voltage, that is cos phi r, that is the angle of Vs plus angle of Is. From that we are going to find the power factor at the sending end voltage, and sending end power, after finding the current Is and cos phi, we are finding our sending end power, that is V in 3 into Vs Is cos phi s. To find the transmission line efficiency, now we have the sending end voltage and receiving end sending end power and receiving end power. We can find the efficiency. So receiving end power divided by the sending end minus sending end power plus coronal loss. Okay, we need to add the coronal loss into 100. So this is how we are going to find the efficiency of our transmission line. Now charging current that required for the line, that is given by V into Y, or we can also derive it by V by Acsr. Second, charging kVA per length of the line, that is equation of kVA divided by transmission line length. From that we can find the charging kVA. And surge impedance loading, that is equal to 2.5 into line kV square in kilowatt, that we already defined in this PPT. Okay, so this is how we are going to find our surge impedance loading. Now 12.5% is the surge impedance loading for the line, so we can easily define 12.5 divided by 100 into kilowatt, that is in step number 30, whatever the kilowatt we have, and kVA per phase. To check the charging current in kVA that we already found of the line per phase, that should not exceed 12.5 percentage of surge impedance loading. Okay, so we need to check this also. Next step is to find the voltage across the insulator nearest to the conductor E1 for finding the string efficiency, that we already seen. So E1 is equal to E into twice sine H 1 by 2 under root of CE cos H under root of CE into n minus 1 by 2 sine divided by sine H and under root of CE, and the value of CE is equal to 1.25 C, and n, that is the total number of insulator disc. And last step, that is to find a string efficiency, is equal to E divided by n into E1. We all know the value of E, and that is the total number of insulator, and S, that is E1, that we already found over here. So this is the total 33 steps for finding the designing of electrical transmission line. Okay, in next video lecture we are going to design, or we can say we are going to see the simple example and designing the transmission line. And here are some Gtu questions that already asked in examination. So questions like explain the surge impedance loading in detail, give the difference between self GMD and mutual GMD, and explain explain the steps for design of electrical transmission line. So we need to define different steps. That's it for the today's lecture, and if you find any kind of query regarding this lecture, then ask me in comment section. Thank you.